Hi, my name is Oleg Selajev, and I work as a developer advocate for the GraalVM team at Oracle Labs. And today we're going to talk about fast and efficient microservices with GraalVM. If you have any questions, I would like you to ask them here during the session, right? And don't hesitate, don't wait until the end of the session. You can just write them in the chat immediately as you have them. And I will keep an eye on the chat. So I will either answer the question right away, or I will just make a mental note about that and then answer them in the end of the session if there is time for that. If there is no time for that and you would like to connect with me and ask questions further after the session, then I almost universally go on the internet by @Selajev. So you can tweet at me, you can email me, you can find me on GitHub and follow me there. Yeah, I think that's the main sites that I'm using, right? So there's definitely plenty of opportunities to learn more about GraalVM or how to build microservices around that, right? So let's get started. This is a short and fast-paced session, so hopefully we'll cover all the material and it will be interesting for you. Right, this is also a technical session, so please do not make any foregoing business decisions based on the contents of this. And note that GraalVM native image technology is available under the early adopter status, so be mindful of that. GraalVM in general. Someone thinks they are seeing a wrong slide. Currently, there is a slide with the GraalVM logo and the other language logos around that. Can please somebody confirm that you see GraalVM slides? Right, very good, very good. Yes, people say that they're saying this, very good. So GraalVM in general, what it is, it's a high performance embeddable polyglot runtime that supports execution of programs in different languages. Currently, there are a number of those. GraalVM includes a compatible JDK, so it can execute all the JVM languages normally and naturally. So that means if you're writing Java, Scala, Kotlin, Groovy, Clojure, and any other of the JVM languages, GraalVM can run programs that you create. And it also can run programs in different other languages like JavaScript, Python, R, Ruby. We have support for WebAssembly. We have support for LLVM bitcode. So that means we can run native languages as well. And all of those can run with high performance. So GraalVM wants the execution of programs to be fast. And it also can be, it's embeddable VM, right? So it can be put into other larger programs, right? Both Java programs and native programs, like if you have a database or something. And also you can write polyglot programs, which means that you can create a system where different components are written in different languages. So this is in general the description of what GraalVM is. It's a very large project. It's a very ambitious project. It pushes the boundaries of what we know of how to create runtimes and virtual machines further. And specifically for Java developers, I think, and for people writing in JVM languages, it offers three main benefits as of right now, right? There are very ambitious plans and the vision where GraalVM could be in the future, right? But right now, you can use GraalVM for the following things, right? It comes with probably the best available just-in-time compiler for very, very many workloads. So when you run a JVM, it includes the just-in-time compiler, right, to make your programs fast. And the just-in-time compiler in GraalVM is special. It's a GraalVM compiler, and it's really, really good. So you can use GraalVM to speed up the execution of your Java applications. GraalVM also includes the native image technology, which is a sort of a compiler for your applications. You can feed your application to the native image utility, right? And then it will crunch it, it will compile it, and it will output the platform binary, the native binary that will not depend on the JVM, right? That will be pre-compiled, that you can just double click and it will start, right? It will offer you a different performance profile. And this whole session, we mostly will concentrate on building the native images and a little bit about the compiler, right? So, and it's a multilingual virtual machine. So you have a Java application or your JVM application, and you want it to understand some other languages. For example, JavaScript could be useful if you want to integrate with some front-end framework or if you want to do some machine learning, maybe you would like to execute some Python, right? And you can run them within the context of your Java application, right? And they will still run fast, and they will still compile just in time, and they have a very reasonable API to include those different languages inside your application. So 3 main benefits, and we're going to talk about the just-in-time compiler first a little bit, just to give you the understanding what GraalVM is and what it looks like when you run your application on GraalVM. And then we dive into the native image compiler and how it works, and see some examples how to make your microservices more efficient that you normally would get from just running them on the JVM. One of the most important things about GraalVM for Java applications is that it gives you an option, right? So it gives you an option to run with a JIT, or to use the native image technology and to compile your application ahead of time. And this is very, very important, very important thing here, because very many people are excited about the opportunity that GraalVM gives for the microservices, for example, and they very often think that GraalVM is mainly this ahead of time compilation thing, and because of some technical implementation details of that, they disregard the ability to run with a JIT, and that is not right. GraalVM can speed up and make your microservices and your Java applications, not just microservices, your large applications as well, more efficient, specifically because it gives you an offer what is the performance profile that you want to get, running with the JIT or running with the AOT. So normally, GraalVM, you can run with the JIT. And it will do the same things that any JVM will do, because it contains a compatible JDK implementation, and it runs based on the open JDK, and it just specifies a different JIT, right? But you also can use native image, right? You can use both. That's the main point of this slide here. How do you get started with that? No. How it looks when you run with the JIT. How you run with the JIT? You run and it executes the Java hotspot VM, right? And then it plugs in the GraalVM JIT compiler with that, using JVM CI, which is the Java Virtual Machine Compiler interface. And it sits there as a top-tier optimizing JIT compiler, which means that when the JVM decides that a certain code path is important enough to be compiled, right, it passes the bytecode to the JIT compiler, and the JIT compiler looks at the bytecode and then says, "Oh, look, this is the machine code that I can do." And through that, we can execute all the JVM languages, right? Java, Clojure, Kotlin, Scala, and so on. And GraalVM is available in 2 flavors. There is a GraalVM Community Edition, which is the open source bits that comes with everything that GraalVM can do. And there is also an Oracle product called Oracle GraalVM Enterprise Edition, which differentiates mainly on performance. So it comes with a more powerful just-in-time compiler. So this second layer here is replaced by a more sophisticated compiler, which will be even faster, and which will include more optimizations. And you can run your programs even faster with that. So that is for the JVM applications, right? Just 2 bottom layers, and it runs based on the hotspot, right? So it does exactly what hotspot does, and it has all the configuration options that you can use for the hotspot, right? So you can limit the memory and whatnot, right? And then for the other languages, what you need another layer, right? So the languages on top of GraalVM do not get translated to the bytecode. There is no bytecode intermediate representation of a JavaScript program, for example. So what it has, there's a truffle framework, which is a framework for implementing languages, and you implement an interpreter for the language using Java and using the truffle API. And then through that interpreter, you can interpret the program, and then at runtime, it will be very efficiently compiled to the machine code. So sort of like that, right? Through the bytecode, there's execution of JVM languages. Through the interpreters written in Java and get compiled at runtime, you can execute other languages. And then there is, on the very right, there is a LLVM bitcode interpreter, which allows us to run native applications. So for example, we can run Doom on GraalVM, which is very interesting. And just recently we published a blog post how you can run COBOL applications on GraalVM and substitute some parts of that with implementation in a different language. So say in JavaScript. So if you're interested about that, you can go to the medium.com/GraalVM and you'll find the blog post about COBOL and JavaScript and learn how GraalVM can run that interesting combination of languages, right? How do you get started with all this goodness? You download GraalVM. You can go to the graalvm.org for the general information about GraalVM and /downloads where you download the things. You pick what distribution you want. We have the binaries based on JDK 8 and 11 currently. So if you're using 8 and 11, you can just use a GraalVM distribution that will be out of the box compatible with that particular Java version. So you download that, you unpack that, you put it on the path, and you run your Java applications normally. And they magically run faster. Well, like they not magically run faster. They're running the same way that your Java applications are running, but then when the code hits the just-in-time compiler, it can output more efficient machine code, and then your application will run faster, depending on the workload. This performance difference could be different, right? So you get started with that. Why is it important to run applications fast? Because performance is actually money. Specifically now, when we run everything in the cloud, performance means faster runtimes mean that you pay less money to the cloud vendor, right? Which is very desirable, of course, right? And you might think, oh, I don't want like any performance improvement. I'm fine with what I have, right? What it is, because it's very relatable, right? But out of the box, getting better performance is always a good thing. And think about that like someone told me this, not metaphor, but the mental calculation, right? How better performance people are like, oh, 2% is nothing, right? Or 2% is not great, or like 4% is not great. But then if you put that in perspective, right? 2% is one monthly salary every 4 years. If you don't want to save 2%, that means once in a 4 year, you can transfer me your salary. And if you haven't done that in the last 4 years, the next slide will have my bank details, and I'm waiting for your contributions, right? So even small performance improvements, right? Even small numbers actually on the long run or on the web scale mean a lot, right? And of course, I'm kidding. Like, you don't have to send me money. Just like for the record, we're recording this. So just to be absolutely clear, you don't have to send me anything at all. But just think about that. Like, or even the small improvements over the large deployments accumulate, and they give you very substantial benefit, right? This is why, for example, large companies like they would like to use fast runtime. So Twitter is one example of the company that is using the GraalVM technology, and they're using the just-in-time compiler to run their Scala microservices, and they're very happy about that. And on the web scale of applications, every performance improvement is a large saving, right? So I'm not sure whether they run on the cloud or build the data centers, but think about that. If you need to build 5 data centers, and then you can save 20% by switching to faster runtime, you can then not build a data center, which is I think a very large investment. So performance matters, performance means money, and you need to be aware of the performance of your applications and try to use the best suitable runtime. So which very often is GraalVM, and naturally GraalVM Enterprise Edition will be the fastest. So if you want the fastest, you should think about that. Oracle Cloud Infrastructure, like the cloud vendor, we migrated. I say we because I work at Oracle, but it's actually them, like they, because I'm not on that team. They migrated some services, some telemetry services for the cloud to GraalVM, and it saw better peak performance. They saw less time spent in garbage collection, and they migrated without problems. They also wrote about that on the blog. But the main thing here is that you can switch and you get faster applications, right? They can be large applications or they can be small applications, but they still most probably will be faster, right? Why do we do that? Well, why do we do that? I have a question from Ivan. What was the features of Java 15 that you can't use right now because it supports Java 11 and 8? Yeah, unfortunately. Thanks for the question, Ivan. Yes, there are no distribution based in Java 15. There's currently 11 and 8. So if you're using Java 15, you currently cannot use the GraalVM distribution out of the box like that, right? So, which is unfortunate. We are looking forward and we're working on enabling more recent Java versions in the GraalVM downloads, but it's a work in progress, right? So I think it's a very reasonable to assume that Java 17 will definitely be there, right? As a next supposedly LTS release, but how long will it take? It's unclear, right? There is work to be done. It's an engineering effort. And as a separate project, right, from OpenJDK, GraalVM moves on its own pace. Java 15, for example, will be active for like what, 4 more months or 5 more months. So it's unclear where the benefit of using that is that large in particular. Right. So back to the performance numbers, right? Why we know that GraalVM is fast? Because we run a ton of benchmarks, right? On every release, on every pull request, a ton of benchmark. And one benchmark suite that I would recommend you to look at is Renaissance. Renaissance consists of, it's an open source benchmark suite, so you can run it, you can look at it, you can contribute benchmarks to it. What it consists of benchmarks from other projects, right? So at the bottom, you can see there are frameworks that are currently modern and used in the application. So you can see there is some Akka, you can see there is some reactive extensions benchmarks, you can see that some other reactive streams there. You can see there is some Neo4j benchmarks in it, right? So what Renaissance wants to be, it wants to be the benchmark for modern Java applications, right? So which is the code that you're using in your applications right now, right? Of course, the best results, right? The best prediction of how the certain runtime will work on your code will be running actually your code. But the second best thing is running good benchmark suites, right? So look at that. We run others as well, and we know the results on those. But GraalVM shows really good results on Java code, even better results on Scala code and Kotlin code and Clojure code, because they're a little bit more abstract. So the strengths of the compiler can shine there a little bit better. But there is performance boost of running applications just like that. So you should try it. You should try it on your workloads, and you should, if you have any questions or anything, just come back to us and, I don't know, report issues on GitHub, and we'll figure out how to make it faster. Right. The one thing is, so this is how you can run your existing applications normally, and you get better results. But on the cloud, it's a little bit different, right? On the cloud, we want to put our applications in very small ephemeral environments, right? We want to package everything in small Docker containers, give it just a bit of resources, maybe like half a CPU or like one CPU and just like 200 megabytes of RAM, and say like, oh, you are a small microservice now, run in this constrained environment. And in that environment, like we want the runtime performance profile to be different, right? So that means that we want it to have a different characteristics for what we think is good performance, right? And if it normally, we talk about performance about the peak throughput, right? How fast things are moving when everything is compiled and everything is warmed up, then in the cloud, we have a different trade-off. So we don't think about performance as much in terms of the peak throughput or the optimized tail latencies, but we mostly care about how fast it starts in these small containerized environments. So we care about the startup speed. We care about the memory footprint, that it is low, because we want to package it very neatly in memory. right? If our memory footprints requires a gigabyte of RAM to just run the process efficiently, then we can only have one application in a gigabyte, right? But if we can run in a small environments, then we can package them and say in 1 gigabyte we can run 4 processes, which makes auto scaling much more efficient. And the packaging, because we need to actually deliver the application to the cloud. So this is how the GraalVM supports those. There is a trade-off in what you want to have, and for the best throughput, you want to use the jet, right? If your application runs for like a period of time and it warms up, it doesn't have to be days; it could be like minutes as well. Then if peak throughput is important for you, then you want to run with a jet, and hopefully with the smartest jet that you can find. And if you want startup speed or low memory footprint, you want to run in the ahead of time compiled mode, which GraalVM offers you. So you can choose which way you want to go and just pick how you want this, right? So now let's talk about the native image facility. How it works: you feed your application into that, and then you get the binary. And that binary could be very efficient, right? So here I have a slide from the screenshot from the Micronaut application that I run. And specifically what I wanted you to note here is I can run it with a small heap, as small as like 60 megabytes. And it starts up really fast, and it's ready to process requests, and it's pre-compiled, so it's ready to serve business requests right out of the box. Why am I showing you these numbers? Or because in the cloud, usually there is a step function how much you pay for the runtimes that you get, right? And the smaller you go, the less you pay. And the smallest runtime environment that you usually can get is something that contains like 100 megabytes of RAM, right? It's a very small container, and you're built by 100 millisecond steps. So if you can fit under the 100 megabytes, 128 megabytes of RAM, and if you can do your work under 100 milliseconds, you can't be built less, right? So that means that after that, there are diminishing returns to the numbers that you get. So what I wanted to show you, that you can run a small application, Java application, that fits into the tiniest runtime that you can get in the cloud. Like the clouds are different, right? But like, for example, I think AWS Lambda has the 128 as a minimal runtime there. So you can take your Java application and fit it in that, and it will work in that absolutely the smallest runtime environment that you can get, which is very cool, very interesting. How do we achieve that? We take all the Java bytecode that will run in your application. That includes your application. That includes the libraries, dependencies that you are using. That includes the JDK runtime library, right? The JDK classes, like, I don't know, Java blank string or like locks or, I don't know, the array list and whatnot. And it also includes the runtime components that come from the project Substrate VM inside GraalVM. Right? So that project contains an implementation of the garbage collection, for example, or like thread shadowing and stuff like that. All that is written in Java. Then all that is analyzed by the static analysis, and the application gets initialized. That means the classes are loaded. That means the graph of objects is created for the like started application. That means that your application sort of is like initialized to a certain point, right? Then the whole application is analyzed, and all reachable code is compiled, and all objects that are pre-initialized are written out into the image heap of the final executable, right? So that means that there is all the code that will ever run in your application is pre-compiled and written out. And some data that will be used in your application is pre-initialized and written out into the executable. That means that the output is self-contained. It doesn't depend on the JVM. It is linked to like the normal operating system libraries like libc and whatnot, or you can build a statically linked executable and link it against muscle C, and then, for example, have the purely like absolutely standalone executable that you can put it in the empty Docker container and run it from there. And it's also ready to do useful work right off the bat. How it works, it operates under the closed world assumption. That means that this analysis that is run needs to see all the bytecode, absolutely all the bytecode. Right? There will be absolutely no code in the native image that wasn't seen during the analysis. We're talking about the Java code, of course, here. That means there is no loading new classes at runtime. If you have any classes to be loaded, they need to be loaded at the analysis time when you build the native image. So if you have like sort of a plugin system, you want those plugins be initialized during the build time. But the benefits of using the this closed world assumption is that all the classes are there. So we cannot care about the class loading or interpretation of the bytecode or any like class metadata for the bytecode manipulation at runtime. So those parts of the infrastructure can go, making the binary, the result much more efficient, because we don't need to, like, for example, waste memory on that. We can remove all the unused classes and methods. And we only can do that because we know that nothing calls them, right? And we only know that nothing calls them because there is no new classes that can be loaded. Because if you can load a new class, then you need to ensure that it can call something that you remove. So you can't remove anything. So you get back to including everything. And also, not having new classes loaded means that we can enable some aggressive ahead of time compilation optimizations that are otherwise not possible. For example, like imagine that if you fix the class hierarchy and you have a method call, you can know exactly that, like say you have a method call in an interface and there is only one implementation of that interface available, you know that that method call will go directly into that class implementation and we can link that directly. If the class hierarchy is allowed to change, then there could be other implementations of the interfaces and then you cannot just link directly and execute that method, right? You have to go through the virtual calls all the time. So by fixing the bytecode, we can enable optimizations. So that's why the binary is efficient. So now, because of the closed world assumption and because of the static analysis, some parts of the application might require configuration, right? So for example, if you use features that are dynamic in nature that cannot be analyzed statically, you need to include hints to the native image builder process that you want to use certain things. For example, if you want to load a resource the name of the resource you pass as a string that can be dynamically generated at runtime, you need to say, like the static analysis cannot say that, oh, I want to include this JPEG file or I want to include this JavaScript file. It needs to, it just cannot tell that because it's static and you provide the full information about the input only at runtime. So without executing code, it cannot tell that. So it needs a hint, and you need to provide a configuration file, which is currently a JSON file that you want to include certain resources, or that you want to use some classes through reflection. That configuration is best provided by a Java agent. So you can run your Java applications normally as a Java application, including a Java agent, and it will record the configuration for the parts that needs to be configured for the runtime, right? So if you use reflection, it will be outputting the reflection config. If you're using Praxis or run resources, it will be outputting the config for that. So you are not, you don't need to configure that by hand. You just run a Java agent and it gets automatically compiled for that. Right. There was a question from Florian, and I will come back to that in a few slides, right? So the benefits of using the closed world assumption are the following. We can get to very low heaps, and we can use very little CPU when actually serving your business applications, right? So this is the example of Micronet application. This is, I think, a hello world, but you can see in the ahead of time compiled mode, you can run the application and serve a few requests. And the RAM usage is at 30 megabytes there, 32 maybe, right? And you also see that CPU is only used when the requests are running, right? So on the right, you have the same example running with a jet, and you can see two things. First, the memory usage is larger, right? And then also there is quite a bit of CPU running because the JVM needs to initialize itself and do quite a bit of class loading. That is a CPU intensive process. You need to verify the classes. You need to load them in memory and start executing them. And also you can see that after 6 seconds there, when you start serving the requests, right, you see another CPU spike. That means that the just-in-time compilation has kicked in, and there is work being done besides just serving the requests, which is all good. But if you limit the CPU, right, if you just give half a CPU to your runtime, then that work can actually accumulates quite a bit. So what you want in small environments, actually the AT compilation, definitely, right? The ecosystem support for this is quite great, right? There are a number of frameworks and libraries that support GraalVM native images. So there is Helidon, there is Micronaut that I will be showing in a minute. There is Quarkus, there are some Spring applications that work. If you do command line applications, Pico CLI is your choice. It's an excellent framework for command line applications, work with GraalVM native images as well. If you're interested in Spring specifically, then I would recommend you to watch this presentation, The Path Towards Spring Boot Native Applications by Sebastian Deluze and Andy Clement. And they talked about how the work progresses for enabling native images for Spring applications, and specifically Spring Boot applications. So you watch that. And now I'm going to show you a Micronaut thing, right? Micronaut is a great framework. It's an application framework that is specifically focused on small applications, the micro, right? So, and the interesting part about that, they use the Java annotation processors to process configuration and do some work before your application is actually run, right? So they can do the dependency injection and configuration. They can do the proxies and bean introspections all before you actually compile the application, right? So, which is very, very interesting. And it also works very well with native images. So that's what I'm going to show you here. And I have just a couple of minutes here. So I'm gonna show you very briefly, right? So I have my application and it looks like any normal microservices application right now, right? So we're using Micronaut. We say that we would like our application and would say Micronaut run our application. What the application is doing is defined here in a controller that we bind to the primes URL. And we just say that we're going to compute some prime numbers. We're going to compute some prime numbers to and from. We just specify the upper bound limit where they want the prime numbers be. And then we just compute them. And you can see that it's very simple, right? The logic is not necessary here, right? We compute prime numbers. That's a sample business logic. I wanted something that consumes some CPU and generates some memory usage, right? It's a very simple application. I can run my Java and I will tell you that this is Java version, right? I'm running on the GraalVM. This is Java 11 based GraalVM. What I can do now, I can do Java minus jar, what is built, libs, primes are cool, all jar, right? This is my Micronaut application here. This is my Micronaut application here. It starts really fast. I can run it. I can open it in my browser, right? So this is the home page for the app, which is not defined. But if we go to the primes, it will output me some prime numbers under 100, right? So this is the URL that I bound my applications on. And when I refresh this, we can see that we get a slice every time, right? So what I can do now, I can stop this. And then I can build the native image here. How do I do this? I do this manually, right? You can use the Gradle plugin for this, but I wanted to show you how to do this, so I do it manually. I use the native image utility, right? And I feed my classes into that, right? And this is the simplest, and Micronaut works really well with native image. So it provides some configuration. When I do native image minus version, it is the same version, and I can run this application and I can build this native image. And it will take 2 minutes actually on this machine. It will take 2 minutes, so I will not do that. But it will output me the primes serial, which I pre-built here. I pre-built actually a bunch of versions here. So let's look at the prime serial. What I do, primes serial, right? If I look what it links against, it's linked against the libc things and no JVM. So it's a standalone binary, and it's currently not compressed. So it's about 70 megabytes, right? Primes serial. Yes, it's currently at 70 megabytes. if you compress that with something like UPX, it will be like 20. And that would be a very nice binary there. And I can run that. I can run that, and it works beautifully. It starts really fast. Look here. So here I'm not limiting the memory, but it starts really fast, and you can see that actually works the same way. So it offers me the prime numbers, which is very good, right? Now, if I want to take this to the next level, I would use the GraalVM enterprise features. I will enable the G1 GC by specifying that I want to use G1 GC with this command line option when building native image. And then it will run with a different memory garbage collection policy, which is adaptive. So sometimes it proves to be very useful to workloads that you have. And a very important and nice feature is that I can use the profile guided optimizations there. What I can do, I can build an instrumented image using the PGO instrument here, command line flag here, and then I can apply load. So I have a test script that applies load to a certain URL for that, and it will output me a profile file. So the just-in-time compiler usually gathers the profile at runtime. The ahead-of-time compiler needs to be fed this profile ahead of time. So we gather that profile ahead of time using this instrumented image, and then we just use the PGO flag, and that native image here, the primes1 G1 PGO, will be much more efficient. There is now time for questions, so I will stop and finish with my 2 slides that I have, and I will not show you actually the runtimes for this, but for this particular use case, for this particular application that you can try later, this one will be much more efficient. So the normal one, the prime serial, will be very efficient, right? It will run very well in the cloud environment because it starts fast. It uses very little memory, but the combination of G1, GC, and PGO will get it much, much closer to the warmed up jet in peak performance as well. So if you want the best of both worlds, you want to use something like this. If you just want efficient microservices, you can use the normal native image, and it will be very efficient, much more efficient than your normal applications in those small environments, right? And if you want just performance for raw performance, then probably using the GraalVM JIT is the fastest, right? You can still configure the memory. You can still configure the GC that you want. You want to use the PGO, and the thing that you want to actually optimize for is the container runtime resource usage to throughput ratio, right? You never want to just go and to absolute numbers, lowest numbers that you can have. You want to have the balance where the application actually runs reasonably fast enough for your business use cases inside your deployment runtime, right? And in everything, in anything, if you want the faster applications, then you want to write small methods, and you want to run with the JIT for the best throughput, and you want to run with native images for the best startup and footprint combination, right? So this is what GraalVM can do for your Java microservices. It makes them fast by running with the best JIT. It makes them efficient by running in this pre-compiled mode. And if you want the absolutely best runtime that you can get, then you probably should look into the Oracle GraalVM Enterprise Edition. It comes with support from the team. It comes with everything included. It's a product, so you need to be mindful of that. But if you just want to use the technology, right? And that technology, we know that it is really good. It is probably better than other choices that you have. So you should be aware that it exists, right? So you can use the open source GraalVM Community Edition bits. It's available on GitHub. It's production ready. A number of companies are using that. You should be looking at that. There are a number of sessions about GraalVM or how to use GraalVM on this conference as well. So and I think this is very ambitious and important project in the Java ecosystem, right? So you should know that it exists, right? So this is my last slide, and now this time for questions. I will first respond to the Florian of the question before, and then if you have any other questions, please tell me in chat. I will be absolutely happy to answer those as well. We still have time, right? So Florian asks, using the AUT will result in large file and prevent Docker from using small layers and overall small footprint. Am I wrong? And it also adds compile time in every development step. Yes, that is mostly kind of correct, but actually this is missing a point a little bit, right? So the binary file that you get is larger than your jar file that you usually have, but you can compress that to very reasonable numbers, like something like a few megabytes, like 20 megabytes for the microservice or something. But it doesn't depend on anything else. So you can build it put into literally the smallest Docker images that are available. And use that. So you will be not using small layers on top of large layers that you have. You will be using reasonably sized layers throughout your Docker image, right? So for example, you can have a distroless image without the operating system with just libc, and it will be something like 10 megabytes or something. And then you can put your 20 megabyte application on top of that. So it will not be the smallest layer, right? But it will altogether, it will be very small, right? And your Docker image, like total Docker image, will be very small, right? Lowering the footprint, right? And about the compilation, yes, if you want to build your native image all the time, you will need to wait a little bit. We are working on speeding up that process, but it's not as fast as just compiling a few Java classes to the bytecode. But you also are not encouraged. I would not encourage you to do that at every development step. You build your Java application and then you compile that to native image, right? Probably you want your CI to do that. Probably you want to do that once before the commit. But I would not encourage you to do that at every step. Right. Ludwig is asking, what's the preferred way to build Spring Boot applications? The plugin seems pretty slow and is still experimental. Is the plugin still the preferred way? Should you use different methods of building images? So Spring Boot applications as GraalVM native images are not actually like in production mode, as far as I understand. There's an experimental project called Spring Boot native images. I'm gonna give you a link. There is a link. I'll send you a link, or somebody in the chat can send you a link. Spring native images, right? It's still experimental, and it describes the way that you should think about the current level of support for Spring Boot applications with GraalVM native images. There are numerous samples that work. There are numerous of stars that work out of the box. Like for example, JPA, JDBC, some templating things. Even Tomcat, I think, for the Spring Boot works out of the box for native images. But also there are some things that you need to configure or you need to be aware of. For example, I think the preferred way to run is to generate the configuration with GraalVM, with this Java agent, to generate the configuration for the reflection and everything. And that is the preferred way, right? So that is how you do that. You probably start with the samples that currently work and not more things. That is for Spring. If you use some other frameworks, and I think for the out of the box, right? You would like to use a star. You want to have this native image working, and then you just incrementally add features to your application, right? So you would start with a framework that actually supports that, like Micronaut, for example, right? And I see Wolfgang linked a blog from April in the chat. April is ages ago, right? April has been very far away. So there is a different link. Yes, I think yes. The com.linux has the right URL. So go through that GitHub page. That is the best answer for the Spring GraalVM native images as of right now. Thank you for supporting me here in the chat. Thank you for all the questions. This is 12:45 my time, which means that our 45 minutes are up. So unfortunately, there is no more time for this. If you have any further questions, I would be absolutely happy to take them online. Just find me on any social media or send me an email. Yeah, I'm open to answering all questions and discussing it further. You can join the community Slack for GraalVM if you can Google that, and just know that GraalVM is there. It constantly gets better, and hopefully it can benefit you and your project as well. Right. Thank you very much. See you around.